try not to move too much. So one of the things you have to do is come up with orbital energy level diagrams. So we'll talk about those. Orbital energy level diagrams. There are two of them. There's single electron. Single electron is 1s. 1s, if we look at the wave function, it's like this. It's just 1/2 wavelength, basically. Then the next one is a 2s. A 2s, what we do is we fit in 2/2 wavelengths, or a full wavelength. So this would be symmetric on both sides. And so this would be the line here. And so for 2s, we'll have positive and negative. We get this. Here we just have this 1/2 wavelength. Over here we have two 1/2 wavelengths, essentially. 3s, how many half wavelengths do you think we're going to fit in there? Well, we're going to fit in 3 half wavelengths. So it's going to look something like this, where we drop down and then go back up and then kind of flatten out here. And so this would be 3s orbital here. These are the wave functions, psi. This would be psi 1s or psi 100. This would be the psi 2s or psi 200. This is the psi 3s or psi 300. This is the same thing. If you recall from Chem 4, there's quantum number assignment there where we figure out the quantum numbers here. Normally this would be psi and L, M. Each side or orbital is defined by that. And so this is kind of taking a slice of the orbital. If we look at the actual orbital, the nucleus is here, and then we're going to have the electron cloud here, but it's too much hassle drawing the electron cloud each time. But that's what you kind of visualize. You visualize this electron cloud where the electron is in there. And this cloud is going to have something called a psi squared. Well, we do psi squared primarily because of this. We can get the probability from psi itself, except if it goes negative, there's no such thing as negative probability. And therefore, we have to square it, otherwise we end up with a negative probability, which doesn't make any physical sense. So that's just going to make this bigger. We've just got this big, this is like a guitar string. You just pluck it, and then you just see this, right? It would be like the first energy for the guitar string. The second energy for the guitar string would look something like this, right? Okay. Now, what happens is when we square this, what happened to the sign? Well, it was where the wave dropped down here, but now we're going to square it, so it's going to be negative squared, which is going to be positive. We lose that phase information. Since we lose that phase information, we have two things that we do. We either color code it. This is often the case. This is usually red. The positive amplitude here. And so we color code it so we know that this was the negative part of the wave. The original wave is here. This is the negative part of the wave here. This is the positive part of the wave here. Again, that makes a difference when we do, because we don't work with single atoms, we work with multiple atoms, and multiple atoms bond with one another. Since they bond with one another, we got to look at how the waves interact with each other. They can interact constructively or destructively. So this is why we keep track of this. If you don't want to use colors, then we usually do this: positive amplitude, negative, negative. This is all positive. And so this is like, you get that. Also, we have the 2p orbitals, which are allowed. The 2p orbitals are the same energy here. We have 3 of them. And the only difference is how they're oriented on the axes. So we'll have one like this, where we have like a full wave, up and down. So we got the peak and the valley here, like this. So this would be psi, and then we do psi squared. When we do psi squared, it looks like this. Now, one of the questions that comes up is this. If we have 0 amplitude here, then we square 0, it still comes out 0. And so these are called nodes. nodes have zero probability of finding an electron there. So if you have an electron, how does an electron get from this side to this side without going through there? And so this is one of the things with trying to visualize electrons. When you try to visualize electrons, how can you get from point A to point B without going through a point in between them, right? And so it doesn't make any physical sense, but if you think about a wave, can a wave occupy, you know, if I pluck the guitar string or something, can it vibrate like this in that sense? Yeah, a wave, a standing wave can be like that. It'll have zero amplitude there. And so if we think in terms of waves, of course it can be on either side of the node. If we think in terms of a particle, how does a particle get from one side to the other side without going through? Because there's zero probability of ever finding an electron. We'll never find the electron here or here. And so there are different ways that we visualize these types of things. In terms of probability dot distributions, this one is going to have this node right here. And so that means that the electron can be inside here. It can't be along this, what we call a spherical node or radial node, and it can be on the outside here. Okay. And so, but it can be nowhere on the node. And this is what we call the 2s orbital here. And so this is 1s, this is the 2s. We have a different type of node over here. The node over here, this is called a planar node. And so it looks quite a bit different. And so when we try to sketch out the electron cloud looks like this. We're going to have what we call a lobe. This is called a lobe over here, and then we'll have a lobe over here. Now, how does the electron get from one lobe to the other? You know, from one lobe to the other, from one lobe to the other, from one lobe to the other, without going through the center? Well, if we think about a particle, that seems to be impossible. And so this is a different type of node. This is called a planar node here. But if we think in terms of wave, yeah, we could have a wave like this, you know, positive, negative, and there's going to be zero amplitude in the center. So if we think about a standing wave, it's easy to see how it can maintain that. There could be energy. So electrons are a bit different. And so normally what people do is they just draw this. So draw this by a 95% probability boundary. So this would be a 1s. A 2s would be larger. And then in the 2s, there's a node that people just usually dash like this. A 3s, you can guess, the 3s is going to have how many nodes? 1, 2 nodes. And so there's going to be like one inner sphere, and then a concentric sphere out here, and then one more out here. This is bigger, it's going to have more nodes. 3p orbitals are going to have more nodes as well. They're going to have, in addition to a planar node here, they're going to have a spherical node too. And the spherical node is just going to slice these like this. So if I drew a spherical node here, then these lobes get cut like this. And so it's going to be like a half, the other part of this here. And so when we look at the pattern, you know, because of these waves, we're adding, like, say, half wavelengths or whatever, however you want to visualize it. The number of nodes, the number of internal nodes is equal to n minus 1. So when n is equal to 1, there are no nodes internal. There's every orbital has an external node, which is called the node at infinity. You know, over here, when n equals 2, there's one node. Although it looks like there's two nodes here, those two nodes are actually the spherical surface here. And this one node here is this actual planar surface here. And then when we go to n equals 3, there are going to be two nodes, you know, two spherical nodes in this case, And for a p orbital, it would be one planar node and two spherical nodes. So when we get to the three p orbitals, the three p orbitals look like this. Where we have the planar node here, and we have a spherical node here. So it just chops them up. And so as we get to higher and higher orbitals, like a 5p, 6p, it kind of looks like a p, it's just it's sliced and diced more, basically.
Can you explain like what the shape next to the 2s, like the atom thing?
This thing?
Yeah.
That's a 95% probability boundary. We usually don't draw, this is called an electron cloud.
Yeah.
This is the 95% boundary. 95% boundary means 95% of the dots are inside that boundary, 5% of the dots are outside that boundary. That would be the 95% boundary.
Can I ask how the 3s looks like? Because it looks like there's like a, like the more condensed cloud in the middle, and then it seems like it has like rings. Yeah, right. So 3s, if we were to draw a 3s orbital, let me draw it over here. We just draw the 95% boundary and then two nodes inside. One node here, another node here. And what it is you have positive amplitude. This is like a drop of water hitting the pond. So you have, let's say you have positive amplitude here. And so it would be, well, it hit the other side. We're underwater. Let's say we're a fish. So we got positive amplitude here followed by negative amplitude. So it'd be like this, right? Followed by, this would be the negative amplitude here, followed by positive amplitude here. So it's just this, like a water droplet wave, that just like this. That's how you visualize that. Now, the question comes up is this. This is called a sublevel. This is the S sublevel, or the L equals 0 sublevel. When we go over here, this is called the P sublevel. P sublevel, or L equals 1 sublevel. So the question comes up, why is there no 1p orbital? If I look at this, I know the number of sublevels. Do you recall yesterday I told you the equation for the number of sublevels? For each n, how many sublevels are there? This is a pattern that we looked at. No. See, this is, well, anyway, this is stuff you don't want to have to cram right before the exam. So if we talked about it last time, you should at least start reviewing so that you can remember. I'm sorry? 9? 9? Like the number 9? Doesn't it depend on the level it's in? Like, if it's...
It depends on what level it is.
If it's 1, there's 1. If there's 2, there's 2.
Wait, so if it's 2.
No, it's we look at the level. The level, this is the level. N equals 1, we call that the level. N equals 2 level. In the N equals 1 level, how many sublevels are there? This is what I did yesterday. In N equals 1, there's 1 sublevel. In N equals 2, there are 2 sublevels. In N equals 3, there are 3 sublevels. Do you see a pattern? What was the pattern in math?
Number of sublevel that's equal to the...
And so why is that? Why that is why isn't there a 1p sublevel? There isn't a 1p sublevel because it violates the Schrodinger equation. Because of the rules for quantum mechanics. The rules for quantum mechanics, these restrictions are there because any other number here violates it. So the first level, second level, third level, this is called the, what was this one called? The N? Principle of quantum number. And what does it tell us?
The level. Energy.
It tells us the level, but it tells us what? The you get it written down?
Energy.
Hmm?
Energy.
Energy, right. So this tells us the energy. And so the higher the N, the higher the energy. Just like Bohr. L,
Angular momentum quantum number.
angular momentum quantum number, and what values does it take?
N-1.
All values from 0, 1 to a max of n-1. And what does it tell us? It tells us the shape. The shape and the energy for multi-electron. And so here, if n equals 1, then how many sublevels are we allowed? We're only allowed one sublevel because of the pattern there, but we could also see it in the Schrodinger equation. If n equals 1, what is our max L? Our max L would be 1 minus 1, which is 0. And so our max L is an s orbital. So when n equals 1, we only have one orbital there, and that's the s. Otherwise, it would violate the Schrodinger equation, and it's forbidden if it violates. If it satisfies the Schrodinger equation, it's allowed. When n equals 2, we're going to have two sublevels. We can see that here, because when n equals 2, then L can be 0, which is an S, and L can be 1, which is a P. And so when n equals 2, we're going to have an S and a P available. But no D. When L equals 3, or excuse me, n equals 3, when n equals 3, then we can have an L equals 2, which is a D. And so I drew that out last time. But the question I want to answer today is this. Why are the S and the P the same energy in a one electron atom? And so let's talk about that. So in a one electron atom, this is why we have two energy level diagrams. We have an energy level diagram for a single electron, and we have an energy level diagram for a multi-electron. You have to memorize them both. In an energy level diagram for a single electron, you need to tell me why the S and the P, the 2S and the 2P, are the same energy. When we have orbitals of the same energy, we say they're energetically degenerate. But the question is the 2S and 2P have the same energy. I can understand, so for example, 2px and a 2py, these are going to have the same energy because all they do is they move this from the x-axis to the y-axis. No change in energy. Or if I go to the z and just move it to the z-axis. So these I expect to have the same energy. But what I don't expect to have the same energy is the s and the p. So why do the s and the p orbitals have the same energy in a one electron atom? And so that's because they have totally different, look at the shapes are totally different, aren't they? You know, when I look at the P, what we do is we draw a 95% probability boundary. The 95% probability boundary looks like this for the P orbital. We have the node here. But the electron can be on the left or the right, what we call lobe, left or right lobe. And it can get there without passing through the center here. Well, waves can do that easily. You know, but a particle can't do that so easily. But we're not going to worry about that. And we don't need to know that so much. But it's a question that often pops up. You know, how does an electron get from one lobe to another without going through the node? And so this is what we need to talk about here. And what we need to talk about is this. When we think about the Bohr model, the energy is going to depend on how far the electron is from the nucleus. The farther the electron can get from the nucleus, this is like a bird. The bird's energy, the farther the bird can get from the nucleus, the more energy it has, right? The closer it gets, the lower the energy. And so the farther, in order to get far away from the nucleus, it needs a lot of energy. And so we have the Bohr orbits. The first Bohr orbit, which we call R1, and then the second Bohr orbit was 4 times, remember, n squared. And so 4 times R1. And the third orbit was how far away from the nucleus? 9 times, and the fourth one was 16 times. So the energy depends. Yeah, and when n equals 4, it's 16 times far away. It's got to be high energy to get that far away, right, from the nucleus. And so the energy is going to depend on the distance. And so what we do is, well, what's going on with the electron here? It could be close by. In fact, the highest probability is when the electron is right on top of the nucleus. Do you see that? And then as it gets farther away, so what's going on with the energy here? You know, because the distance, it depends. It could be super close or it could be super far. And so what do we do in that case? Do we take the average? No, we don't take the average. I mean, is there such thing as an average distance there? No, what we do is we think in a different manner. And so when we think about energy, we typically think about something called the effective distance. And so the energy of the orbitals, energy of electron in single electron energy level diagram. This we abbreviate ELD for short, although people don't usually abbreviate that. Depends on the effective distance. Actually, I probably should write in caps. It's easier to read. But it depends on the effect. And then when we look at the 2s, if I look at the 2s, where's the greatest probability of finding the electron? Where's the greatest probability, the highest probability of finding the electron? This is psi squared 1s, this is psi squared 2s. Can you tell me where the greatest probability of finding the electron is? Right at the peak, right at the nucleus. So if these two have the greatest probability of finding the electron right at the nucleus, then what's the difference in distance? Well, this one has maybe a little higher probability. It might be further away. You know, but how do we figure out what the energy is of such thing? And so what we do for this is we have to use something called the radial distribution function. And the radial distribution function is this. When I do the electron cloud here, this is the 1s here. If I do the electron cloud here, where am I going to find the most dots?
In the middle, it's just to the...
I would say right against the nucleus. Wouldn't you say you're going to find the most dots there? But it turns out it's not. It's not right against the nucleus, because what we do in the radial distribution function is we divide this into spherical shells, each with the same thickness. Etc. I'm not going to draw all the shells out. Now, the first shell is the closest to the nucleus. And then the next shell, these are like onion layers. The next shell would be a little bit farther, a little bit farther, a little bit farther. Would you expect the most dots to be found in the first shell surrounding the nucleus?
No.
Yeah, that's the correct answer. No, why?
There's more space on the other ones.
Yeah, there's more, we'll just say volume on the other ones. Well then, what about the last shell? The last shell is going to be the largest in terms of volume. Would that one have the most dots? Why not the shell way out here? This is not the last shell. The last shell will be at infinity. But why not the shell out here?
It's a lot of energy to be on the left.
No, we're not, the shells aren't energy, the shell's the distance. Each shell is an increment away from the nucleus.
Too far?
What does that mean, too far?
It's too far from the nucleus.
Out here, is there much probability of finding the electron? No. And so, but the radial distribution function, it optimizes two functions actually. The first function is the probability. The probability is the highest at the nucleus. This is psi squared. And so you would expect the greatest probability, as far as the greatest probability in terms of distance, would be right against the nucleus, like 0 picometers away. But then we have to look at the volume of the shell, because the first shell here is quite small. And it being small means it has very low volume. As we get to bigger and bigger shells, the volume of the onion layer, and so the hollow shell. And so what the radial distribution function says is this: the greatest or most probable distance is going to be right here. We're going to have, in this shell, we're going to have the greatest number of dots. And therefore, that's the most probable distance. Do you know what that is? What was the first Bohr orbit? Does somebody recall what the first Bohr orbit was in picometers? What was the length of the first Bohr orbit, or radius of the first Bohr orbit in picometers? 53 picometers. I'm not going to make you memorize that. But, you know, if you're just reading through your notes, if you read through your notes every day, then it's a number that sticks. We talked about it a couple of days ago, and maybe once or twice, you know, like 4 or 5 times, 10 times, it sticks. So I don't intentionally memorize those numbers, but after you see it like 10 times, it's pretty easy to memorize. But anyway, that's 53. Do you know what the most probable, this is from quantum mechanics. Do you know what the most probable distance is? 53 picometers. Do you see why we get the same energy for the 1s orbital as we got for the first Bohr orbit? Because they both have the same effective distance from the nucleus. The first Bohr orbit was at 53 picometers, and that was it. In quantum mechanics, the most probable distance is 53 picometers, so it's going to have the same energy. Okay, so we could do this. For the 2s orbital, it's going to be, you know, the most probable distance is going to be, do you know how many times this, or approximately where it's going to be? N squared. Around the Bohr radius is n squared r1. So n equals 2. 2 squared is 4. 4 times r1. 4 times, this is r1. 4 times r1 is about 200 picometers. So the 2s orbital is going to have the most probable distance of 200 picometers away. So it's acting like a Bohr orbit, but it's not a Bohr orbit because we look at it totally differently. We have to do all this quantum stuff, you know, with the Heisenberg and de Broglie and that kind of stuff. And so does that mean the 2p will be the same? And so let's take a look at that here. This works. Believe this works. Okay, so this is the radial distribution function for the 1s orbital. This is what we talked about. The most probable distance is right at the p. You know, the highest probability is right at the nucleus, but the most probable distance is right at the peak. So you need to know the difference between probability, chi-squared, and RDF, the most probable distance.
What's that variable with the,
You don't need to know this.
but what's the name of it? It's gonna bother me.
This psi. This is chi-squared. It's the wave function. Psi is also the orbital. And so I draw it differently. I draw it like this.
Yeah, but how do you pronounce it? Like your sine, psi,
Oh,
like your sine?
PSI.
Okay.
Psi. So this is probability and then the distance, the volume. And so it's two functions being maximized. You're trying to maximize the probability function, the black, and you're trying to maximize the red function here, the volume. And so we do it here. Now, 2s is going to have a node here. So at the node, there's zero probability of finding the electron, right? But you can see there's a little hump here.
I'm sorry, do you mind the two things you said, like not to confuse, like the most probable distance?
Chi-squared and the RDF, radial distribution function. Sometimes they look the same, and so they can be confusing. And so people get it confused sometimes because this, look at this, is chi-squared R squared, right? And then, you know, one has a peak right at the nucleus, the other doesn't. And so we're looking at the radial distribution function now. So we're going to move away from psi squared, and we're just going to look at RDF for right now. When we look at the RDF here, we see a small hump here, so there's good probability the electron is around here, but where's the peak in probability? It's out here. And this is going to be about 4. This is about a half angstrom. This is going to be, this is about 50 picometers here. This would be about, how many did I say? 200 picometers here for the 2s. Now, what about the 2p? When you look at the 2p, where is the most probable distance for 2p orbital? It's closer. If the most probable distance is closer, shouldn't it have lower energy? Shouldn't the 2p be lower in energy than the 2s because it's closer? And it turns out it's not. Because we have to think in terms of the shape of it. And so here, so the question comes up, why is the 2s and the 2p the same energy? Because when we look at the RDF, you know, this is about 200 picometers in the RDF where it peaks. And so we look at the RDF, and the RDF, here's the nucleus here, there's a small hump here, a node, and a big hump here. And so let's say this comes out to about there. But whereas when we look at the 2p appears to be closer. And if the 2p is closer, then it should have lower energy. So this is the 2p here. And then when, oops, this is not the 2p, this is the 2s here, and let's draw the 2p in a different color. So I'm going to draw the 2p. The 2p has a node right at the nucleus, and so there's no node out here. This is just one of the lobes out here. And so we'll just draw it here. And let's try to draw this somewhat. So when I look at the 2p, if the 2p, the most probable distance is closer, it should be lower in energy, correct? Yes, correct. That's the electrical interaction. The farther it gets away, the higher in energy it gets. But it's not, and the reason it's not is this. Because when we look at the nucleus here, let's say, and then we have an electron out here about 200 picometers. This is 200 picometers. It can be anywhere in the sphere. Here. And so this is just one dimensional. We'll just take a slice, but in 3 dimensions, this is just a sphere. It's not like a planetary orbit. You know, a planetary orbit would be in a plane. This is anywhere along the sphere. Here. Whereas when we look at a 2p, yes, a 2p is closer, but what? Oops. It's only going to be here and here. And the reason is because of the shape of the orbital. When we look at the orbital is like this. So it appears it's less than 200, but it doesn't go over the entire sphere. And so if you were to take this and then distribute it over the entire sphere, then its effective distance is the same. So in other words, it's limited. So even though it has a closer, stronger interaction, it's only limited to this lobe and this lobe. It's not all the way around. And so what that means is this. If we were to normalize this and distribute this, then we get about 200 picometers of effective interaction, electrical. These are electrical interactions. And so this is normalized over the sphere. Shouldn't say. I'll just say distributed. So we can be at this distance with this energy, or we can be closer, but we have to limit the area of interaction. If you've done some physics with surfaces and surface potentials and electricity and magnetism, this is some type of stuff you would do, like distributing the charge over surfaces. And so the surface here, the black surface, is much smaller, and therefore it's going to have a stronger interaction. This black surface is much larger, and therefore it's going to have a weaker interaction. Does that make sense? Anyway, you don't need to know. You don't have to do the calculus for this. All you need to know is that the 2s and 2p have the same effective distance, even though the radial distribution shows the most probable distance is different. That's why the 2s and the 2p are the same energy. And this goes on, I can throw in the 3s, 3p, 3d. It shows the same type of behavior. In fact, maybe I'll just show the 3. There are RDFs here. You can just look those up if you're interested in that. Okay. So the same thing happens. The 3s, the 3p, and the 3d are all going to have the same effective distance, even though the most probable distance is this is going to be closest, this is going to be further, and this is going to be the furthest out.
I was wondering, is it the same because 2p is like a smaller, like it's more concentrated?
Right, it's smaller, exactly. That's why. Whereas an S is big, it encompasses the full.
Yeah. So it's like has a larger volume for 2s, but it's like less concentrated because of that larger volume, and 2p has, it's more
exactly
concentrated because of its.
So if you're standing on the surface of the Earth and you see the whole sky, then there's nothing blocking it. But here, if you're standing on the surface, you're standing in a cone, and if you're looking at the cone, you aren't getting all the sunlight from the cone.
So it's because they're inversely related in both those aspects.
Yeah, kind of. Not exactly that, but we're just limiting the area. So if you don't see the full sky, you're not going to get all the sunlight. And so you'll need a brighter light bulb. That's why it's a little bit closer to get the same energy. And if you see the full sky, then it doesn't have to be as bright because you're getting light from all directions. But if you're in a cone and you want the same energy of light, then it's got to be a little bit brighter. It's got to be a little bit more intense. That's one another way. But anyway, the point is that when we look at the quantum mechanical model and we look at the Bohr model, we get the same energies. And so the energies for this is exactly the same. So from the Schrodinger equation, we get that the energy depends on n and z. And it's just going to equal Z squared N squared. No, it's not N squared, sorry. Z squared, what was that? R sub H over N squared minus. And so when we look at the hydrogen atom, Z is 1. And so we get the exact same energy equation from the Schrodinger equation that we got from the Bohr, but the picture is totally different. Bohr is just a simple orbit, whereas in quantum mechanics it's a lot more complex. Now, the reason that Bohr wasn't able to predict anything with more than one electron was because of this. When we have more than one electron, this is for a single electron.
What's the subscript next to R then H?
This is H. R sub H is the Rydberg constant. 2.178 times 10 minus 18 joules, but you don't have to memorize that. For multi-electron atoms, the energy depends on N and L. I'm not going to write out the equation for the energy. We get the energy equation from the Schrodinger equation. And you don't need to know because we're not going to calculate any of these energies. All we're going to do is we're going to do it very qualitative. It's going to depend on N and L. And so first off, we need to know what that dependence is. So this is, you don't have to understand all the details. The most important thing, and this is, I know that people want to understand everything from first principles physics, starting off with Coulomb's law and then building up to full quantum mechanics. But it's going to be too much of a bear. So at the bare minimum, what you need to know is how to draw this and just memorize how to draw this. We need to memorize how to draw this up to the what we call the fourth shell. And so this is the 1s. And a lot of people, I made my Chem 4 students do this, I think. And so you don't need to know all the quantum mechanics behind this. All we need to know is it goes 1s to 2s to 2p, and then what? 3s. Now the jump from 1s to 2s is going to be big, but what about the jump from 2s to 3s? It's going to be smaller. And then to the 3p. And then you have to memorize this. It doesn't go to 3d. Where does it go next? 4s. And then, where? 3D. And then? 4p. And then it doesn't go to 4D. Where does it go? 5s. So 5s starts the next shell. And so we call these shells of orbitals here. And so this would be the first shell. This would be the second shell. This would be the third shell. The third shell only has 2 subshells. Normally the third shell should have, the third energy level should have how many subshells? 3, but the third sublevel is actually in the fourth shell. And so the third subshell of the n equals 3 is actually in the fourth shell. And then we have the fifth shell. Each shell begins with S. But there are an infinite number of shells, so how do we figure out? Like, let's say I'm on the 10th shell. Okay, if n equals 10, I know there are 10 sublevels, but those 10 sublevels aren't all in the 10th shell. And so how can I figure out what's in the 10th shell? So I know when n equals 3, I have 3 subshells. There's 3 sublevels. Subshell and sublevel are the same thing. So I have 3. Are they all in the same shell? No, only 2, the 3s and the 3p. Well, when n equals 4, I have 4 sub levels, the 4S, the 4P, the 4D, and the 4F. Are they all? No, they aren't all in the 4th shell. What's in the 4th shell?
4S,
The 4S and the 4P, and the 4D go into the 5th shell, and the 4F go into the 6th shell. So how do I figure this out? Well, that's easy because there's a pattern. And this is the pattern that we use to figure out what's in the shell. Each cell begins with an S. Each of these adds 1 because this, remember the max, this is L. L equals 0, 1, 2, 3, 4. The max L is n minus 1. And so here we max out at 0, here we max out at 1, here we max out at 2, here we max out at 3. And so that's one of the patterns. The other pattern that we see is how they fill. We fill these like this. And so 1S, that's the shell. Then the next shell begins with 2S. And then we have a 2P here. The next shell, actually, let me connect these. The next shell begins with 3S. And then we go up here to 3P and then stops here. The next shell begins with 4S. Actually, I probably should do these in different color. 4S starts the shell, and then we go to 3D, 4P, and then we have to stop at 5S because 5S will begin the next shell. And so we could figure out and so we could build this table to all the way to infinity if we wanted, but it would take too much time, right? But it's a simple pattern. You also need to know the quantum numbers. So 1S, what are the quantum numbers here? NLM.
1, 0, 0.
2S,
2, 0, 0.
3S,
3, 0, 0.
4S.
4, 0, 0.
Good. 5S?
5, 0, 0.
All right, perfect. 100% perfect score. How about the 2Ps?
2, 1, negative 1. 2, 1, 0. 2, 1, 1.
Okay. 3P?
3, 1, negative 1. 3, 1, 0. 3, 1, 1.
Here we see we have different M's, the magnetic quantum number. And so each of these corresponds to a different orientation. And the number of M values tells us how many orbitals. So we have negative 1 is 1, 0 is another, that's 2, and 1 is 3. So we have 3 orbitals at 3 different orientations. And the 4P?
What? 3, 1. Wait, 4, 1, negative 1. Sorry.
4, 1, negative 1.
4, 1, 0.
4, 1, 0.
4, 1, 1.
4, 1, 1. 3D?
3, 2, negative 2.
3, 2, negative 2.
3, 2, negative 1.
3, 2, negative 1.
3, 2, 0.
3, 2, 0.
3, 2, 1.
3, 2, 1.
3, 2, 2.
3, 2, 2. Etc. When we get the 4Fs in there, then L is equal to, the 4F orbitals will have 4, 3, negative 3, etc. So you need to build up the multi-electron to the 4th shell. So you need to memorize this to the 4th shell. So either just memorize it or derive it. It's nice to be able to derive things, because if you could derive things, of course you can memorize this. Lots of people do. But if you know the pattern, then you can do more,
These are supplements. So this is like 0.
So we could do more if we know the pattern. So for example, this. What are all the orbitals with n equals 5. First off, I'll ask myself, how many orbitals am I looking for? Hmm?
5?
No, I'm looking for 25 orbitals. So I want to figure out what of those 25 orbitals are. Remember, this is a pattern from Tuesday. This is n squared orbitals. So what are they? 25 orbitals, that's not too bad. We can do that quickly. So I'm going to just do that quickly here. So when n equals 5, I can have what L values? No.
1, 2, 3, 4.
No.
0, 1, 2, 3, 4.
0, 1, 2, 3, 4. What are my m values that are allowed? If I'm allowed plus to minus 0, that's 0. I'm allowed, -1 to 1, -1, 0, 1. I'm allowed
-2 to 2.
-2 to positive 2. I'm allowed -3 to positive 3. I'm allowed -4 to positive 4. So this tells us the number of orientation. The orientation we get from the Schrodinger equation. It's going to tell us the shape and how it's oriented. L tells us the shape. The shape of this one is S, P, D, F, and then what comes after F?
G.
G. You only need to know the S, P, and D. The S is simple, just one. P, this. D is this, or there's one more. It looks like a P, but it has a hula hoop around it. F are more complex. They have more nodes, so it slices up the lobes more. And G is the same thing. It's sliced up more. The number of orbitals is here. Let's count it. Did we get all 25? This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. We got all 25 orbitals in them. And so what are all the 25 orbitals? Well, the first one is going to be 5, 0, 0. The next three are going to be 5,
-1,
5, 1, -1,
5, 1, 0,
5, 1, 0, 5, 1, 1. The next, how many is this? Orbitals. 1, 2, 3, 4, 5. In fact, it's easy to tell based on L. If I have L of 25, how many orbitals do I have? L equals 25, how many orbitals do I have? Two ways you can do it. You can count it by hand, -25, -24, -23, -22, or you can use a mathematical pattern. Do you see a mathematical pattern? I wrote this on
2n plus 1.
Tuesday. Oh, what's that?
2n plus 1.
2L plus 1, so the answer is 51, right? 51. So here, this 2L plus 1, 5 orbitals. 2L plus 1, 7 orbitals. 2L plus 1, 9 orbitals. And so we try to, if you know the patterns, you can do a lot more than just memorizing it. And so anyway, do you see this is going to be 5, 2, -2, 5, 2,
-1.
etc. And then let's just do this last one here because this is new. We're going to have 9 orbitals, so we need to draw 9 lines. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we have to label these. This one is going to be a 5, 4, -4, followed by a 5, 4, -3, 5, 4, -2, 5, 4, -1, 5, 4, 0, 5, 4, 1, 5, 4, 2, 5, 4, 3, 5, 4, 4. So this is why people make you memorize the rules for quantum numbers, because if you memorize the rules for quantum numbers, you can generate the entire energy level diagram. Not that you'd ever want to do it, but you could do it. And the energies are going to be qualitative. You know, we're not actually going to do quantitative calculations. These are the 5G orbitals here. And we'll have 9 different 5G orbitals. They're different. They're all the same energy. They're different in their orientation. These are not the same energy. We expect the 5s orbitals to be the lowest in energy, followed by the 5p, followed by the 5d, and the 5f are going to be higher, and the 5g are going to be the highest in energy. And therefore, they aren't necessarily in the same shell, you know, because of the splitting. We call this the splitting of the energy levels. So what happens is we were energetically degenerate, and then the energy levels split. Now, why did the energy levels split? Because isn't the effective distance, didn't I just say the effective distance for all these is going to be the same, even though the RDF is going to be different? Didn't you just hear me say that? So then why are the energies different if the effective distance is the same? So all these have the same effective distance, which is about, what's that? How far away is that going to be? How many times R1?
53 times.
No, yeah, 53 picometers times what? R1's 53 picometers.
25?
25, yeah, this is going to be about 25 times R1 away. So all these are about 25 times, well, they are 25 times R1 away, effective distance, you know, depending on the light and shading. And so if they're all the same effective distance, didn't I just say with the one electron, you know, all the n equals 5, in the one electron, all these are the same energy. Exactly the same energy. But in multi-electron, they aren't. They start to split. And so this is multi-electron. In single electron, all the energies are the same. And so the effective distance is the same, but why would the energies be different then? And so the answer to that is this is the energies. Why do the energies split? And so the answer to why do the energies split is because of this, because of shielding. Shielding our inner electrons block some of the sunlight from the nucleus. The sunlight would be the positive charge from the nucleus. And it blocks some orbitals more than others. Like, not all the orbitals are blocked the same. And so this blocks nuclear charge. And we call that the difference in there. I'll just say first, let me just say, there are differences in the effectiveness of shielding depending on the orbital shape. So what we look at is something called penetration. And so this topic is called shielding and penetration. In fact, that RDF that I got off the internet here was from a tutorial on shielding and penetration, it looks like. Let's take a look. Yeah, penetration and shielding. Shielding's the problem. And we can get around that problem via penetration. And so what's the difference? Let's take a look at the RDF here. When we look at the RDF here, the 1s electron, if we have a 1s electron, let's go to a 2 or 3 electron species. Let's look at a 3 electron species, like something like lithium as an example here. And let's look at the RDF here. Lithium has 2 1s electrons. We call it 1s2, and then 2s1 is this electron configuration. I think you guys remember electron configurations from Chem Intro. If we have 2 electrons in the 1s, then that's going to occupy this here. Now, if I put an electron in the 2s here, what happens is the 2s doesn't see the full nuclear charge, because the 2s electron is going to be out here, the 2s. This is the 1s. So if I have an electron out here, and I have 2 electrons out here, then Z is +3, or Z is 3. There's, in other words, there's +3 charge here. That's Z. But what happens is that the 1s electrons see that. And so these don't really shield each other much. And so we have something like Z effective. Once in a while, this electron will partially block this. But Z effective is going to be closer to 3. It's going to be slightly less. It's going to be about 0.3 less. But Z effective is what that electron sees. And then we have Z effective over here. The Z effective for this electron is going to be a lot less. The Z effective for this electron is going to be about 1. Why? Because the 3 positive charges are, 2 of them are canceled out by 2 negative charges here. And so Z effective is essentially 1 because these 2 negative charges block out 2 of the positive charges here. Whereas over here, Z effective is going to be much closer to 3. It's going to be a little less, just slightly less than 3. Because once in a while, this electron will block it. But, they try to stay away from each other. However, this electron can sneak in here. This is called penetration. If this electron sneaks in here, then it's going to see higher Z effective. So if this electron can penetrate through here and end up here, do you see the Z effective is going to be a lot bigger? Yes? No? Yeah, because there's less likelihood that these 2 electrons are going to shield. So the amount of Z effective that the outer electron experiences depends on how many inner electrons there are and how penetrating this orbital is. And so this is 2s, sorry. The 2s I drew wrong. Let me fix my 2s. The 2s, remember, has this node and this little hump, like this. And so if this electron can get past the node, which it can, and then over to here, let's say move it here, then it's going to see a lot more of the +3 charge. How about a 2p electron? So normally it wouldn't matter. In lithium, does the electron go in the 2s or the 2p? Well, you think, oh, the 2s and 2p, they both have the same effective distance. They both have the same effective distance, but they have different penetrating abilities. So even though 2p is closer in terms of most probable distance in the RDF, it's less penetrating. Do you see what is the probability that the electron can penetrate through the 1s electron cloud and get right up to the nucleus? Is it a very high probability? No, it's a very small. If you compare the probability of the green, it's much higher than the probability of the red. And so this is what we say. An s orbital is much more penetrating than a p orbital. Therefore, the s orbital, the 2s orbital, is going to be lower in energy than the 2p orbital. And so if I came to a choice, would the electron rather go into 2s or would the electron rather go into 2p? The electron would rather go into a 2s. It would rather go into a 2s because the 2s can get closer to the nucleus. It's more penetrating. And therefore, the 2s is lower in energy than the 2p. And so we can draw the 2p here. The 2p is kind of what I had up earlier here. Even though the 2p has a much closer, more probable, you think it's lower in energy, but it's not. One, because they both have the same effective distance, and two, because of the penetrating ability. The penetrating ability for an electron to move over here is minimal. And so this is what we say. We say that the 2p is more penetrating than the 2s. What if there are no 1s electrons? If there are no 1s electrons, then it doesn't make any difference because they both have the same effective distance. But since we have more than one electron, then we have to worry about shielding. If we have to worry about shielding, then we have to worry about penetration. And this is why we see the splitting of the orbitals in the sublevels. Okay, now, so what we want to do is we want to be able to use some of the patterns in quantum mechanics to answer some questions. So for example, is the, let's say, is the 100 99 orbital allowed or forbidden? Is that allowed or forbidden? Yeah, is the n allowed? Yeah, that n is allowed. Is this L allowed? Yeah, this n minus 1. Is this m allowed? Yes. So this is allowed. When n equals 100, how many orbitals are there with n equals 100?
100 squared.
Yeah. Would be 100 squared. Would be 10 to the 4, which would be 10,000. How many sublevels are there?
Maybe 20,001.
100 sublevels. Oh, you can go back and talk about it. How many, this is the 99 sublevel. How many orbitals are there in the 99 sublevel? This is one of the orbitals. How many other orbitals? Plus how many L equals 99 orbitals are there?
199? Isn't it like 2L plus 1?
Yeah. So 2 would be 198 plus 1 is 199. Correct? It would be 199 total. 199 total orbits. What are they? I'm not going to make you do that, but there would be 199, 99. What's the next one? 199, 98. We're going plus to minus. It doesn't matter if you go minus to plus. Dot, 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 all the way to 199 minus 99. It'd be a pain to write them all out, but you could if you needed to, right? And so I mean, we don't need calculus. In order to solve the Schrodinger equation, you need differential equations. And as far as differential equations go, it's an easy differential equation to solve. But you don't need to do that because we can figure out qualitatively everything. And that's what we need just for right now. And so the spectrum is much more complex. When we look at the line spectrum for hydrogen, it's a lot more complex than that, because we see a lot more potential transitions occur. So I'll just draw this. And so the potential transitions that are going to occur are things like this. You know, here, or possibly here, 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 and then we're going to get lots of lines in the line spectrum. Do you see that? There are some certain rules that occur, but each of these corresponds to absorbing or releasing photon, because it can either absorb energy going up or release that energy coming down. So an easy one is like the sodium lamp. The sodium lamp is this. When we look at the sodium lamp, it's just this is 1, 2, 3. It's just a 3p electron dropping down. So if we have an electron here, we drop down here, it emits yellow for the sodium lamp. And so the sodium lamp excites electrons. It's sodium vapor is inside there. It doesn't take that much energy. It's very efficient. And so sodium lamps, they use them for street lights because the energy consumption is very low. However, the color of the light is really weird. You know, the color of the light is this kind of orange haze to it. And so, but it's adequate for lighting up streets. Now they have LED lights, but they used to use a lot of sodium vapor lamps. And what happens is the electron gets excited at the 3p, drops down to 3s, and emits yellow. Actually, there are 2 yellow lines, because the next thing we're going to look at is electron spin, because the electron could be spin up or spin down, and it gives 2 different lines depending on if it's spin up or spin down. And so quantum mechanics, from that viewpoint, is very successful. Because it allows us to predict things like the spectrum of more complex atoms, that is multi-electron atoms. Okay, the next thing we're going to do is we're going to fill the orbitals with electrons. Filling orbitals with electrons. And the first thing we're going to do is we're going to just do the ground state versus excited state. So if in a sodium, if an electron is in the 3p, that's what we call an excited state, because normally the electron should be in the 3s. And so somehow the electron got excited up to the 3p. When we fill these, it could be an excited state or it could be ground state. So we can see what potentials are. So ground state means lowest energy. Lowest energy doesn't mean it's all the way down at 1. Because the lowest energy for this one should be in the 3s. There are already electrons in the 2s and 1s. So, lowest energy configuration. And the excited state is we could have a higher energy configuration. But it still has to conform to quantum mechanical rules. So when we fill orbitals for the ground state, we pay attention to some rules. The Aufbau principle. The Aufbau principle is start from the lowest and then go up. So you fill from the bottom up. Unless we're looking at an excited state. If we're looking at an excited state, we might populate higher energy states here. That's off-bound. The next thing we need to look at is the Pauli exclusion principle. This comes from quantum mechanics. The Pauli exclusion, there's a fourth quantum number called spin. And there are only two possible values for spin. It could be spin up, or the electron can be spin down. This is entirely quantum mechanics. This was a prediction made from quantum theory. The electron can only have two spin states. It was a prediction made by quantum mechanics, and then physicists went out to test it. And they tested it using the Stern-Gerlach experiment. The Stern-Gerlach experiment's talked about in our book, but I'm not gonna, you don't have to memorize what it is, but let me just briefly talk about it. If we shoot electrons through a magnet here, it depends if the north pole of the electron's up or down. So the electron splits into two beams, corresponding to if it were spin up or spin down, how it interacts with this external magnet. And so Stern-Gerlach went and tested it, and they shot electrons through here and got two beams and hit the detector, and then they won the Nobel Prize in physics for that, the detection of the spin of the electron. But anyway, all we know, why are there just two spins? Well, that's for the electron. Other things can have more than two spins, and some things have no spin. So for example, hydrogen nuclei, the proton, have two spin states too, spin up or spin down for the hydrogen nuclei. And that gives rise to another Nobel Prize winning thing, and that was called nuclear magnetic resonance. It was pretty easy for Stern-Gerlach to measure the spin up and spin down state for electrons. But to measure the spin up and spin down states for hydrogen atoms was much more difficult. So the first team that tried it failed. They failed, it turned out, not because the physics was wrong, they failed because the amplifier was too weak. The second team that went, they had better electronics, better amplifiers. And the second team that did it detected the two spin states for the hydrogen atom. And you would think that both teams would be awarded the Nobel Prize, but the first team was completely ignored for the Nobel Prize, and the Nobel Prize was awarded to the second team. And so that was one of those stories that goes around that a lot of people thought was quite unfair, you know. But anyway, that's life. So life is like that. So that led to something called nuclear magnetic resonance. They take the nucleus of a hydrogen atom and flip it like little bar magnets. And so when you go into an MRI machine, that's what they're doing. They're trying to take your little magnets and your hydrogen atoms in water and flip the magnet. So it might be north pole up, and then they try to flip it, you know, south pole down, or north pole down. And by the energy that it takes to flip it, then they can determine where it is in three-dimensional space, because they don't use what's called a homogeneous magnet, they use a heterogeneous magnet for that. But the spin is important. This came from quantum mechanics, and that's what we got. And so when it's spin up, the Schrodinger equation assigns a variable 1/2. When it's spin down, it's minus 1/2. And we have other things that are quadrupolar. They have 4 magnetic moments or higher. This is dipole. Dipole's 2. Quadrupole would be 4. So you'd have 2 north poles and 2 south poles, etc. So the Pauli exclusion principle says this. NLM defines orbital. And so this is like the address of the electron. A lot of people think of NLM as the address for the electron. So the electron lives there. It might not live there permanently, but it's there for right now. And so then we have S. S is the spin. And so it tells us, is it right side up or upside down in that? The right side up and upside down is meaningless unless you have like gravity. Right side up and upside down is meaningless for magnets unless you have an external magnetic field. If there's no external magnetic field, then it doesn't matter. There's no right side up or upside down. It's only when you place it into a magnetic field that it makes a difference. So these are the 4 quantum numbers that define an electron. 4 quantum numbers define an electron in an atom. And so what the Pauli exclusion principle says is that no 2 electrons in the same atom can have the same set of 4 quantum numbers. So no 2 electrons in the same atom can have the same set of 4 quantum numbers. And so let's go to 1, 0, 0. If we have 1, 0, 0, then there are only 2 possibilities. It could be plus 1/2 or minus 1/2. We can't have 2 plus 1/2 because that would violate the Pauli exclusion principle. So you can have plus 1/2 or minus 1/2. And so what that does is it sets the max occupancy. The max is 2 electrons per orbital. We can't have more than that. It's a violation of the Pauli exclusion principle. All right, the last thing that we pay attention to is Hund's rule. Phil degenerate. What does degenerate mean again?
Empty, maybe without
I'm sorry?
empty? Or
Not empty.
Same energy.
If it's empty, we just say empty.
Same energy?
Same energy. Fill degenerate orbitals singly with parallel spin. That turns out to be the lowest energy. So let's say I'm looking at the 2p. What I do is I'll do it like this. 1, and then the next one should go over here. This would be Hund's rule. Is okay. How about this? Is this a violation of Hund's rule? If I put the second electron in the third rather than in the middle. Is that a violation or is that okay? This is okay. This is okay. What if I do this? What if I do this? Is that okay or not okay? This is okay. There's no upside down or right side up unless there's some kind of external field. We don't know. Uh-huh.
I'm just staying on top of it because I thought you're supposed to do like each one before first and then skip to the other.
Why is top one okay? Because we have to look at the orbitals here. The difference between these 3 orbitals, and so I'll dash these differently. Is this. The difference is one's on the X, the other's on the Y, the other's on the Z. So does it make any difference if it's on the X, Y, or Z? No, they're all the same energy. So I could put 1 electron in the X. Does the next electron have to go in the Y, or could I put it in the Z? I can put it in the Z, it's not a problem. Because it's the same thing, it's 90. If I put it in the Y, it's 90. There's no difference. They're all what we call orthogonal, that is 90 degrees relative to each other. And so it makes no difference here. In fact, I could have done this. I could have left the first box empty. Here, this is the same energy. Uh-huh.
But would it matter if there was like more than 3? Like,
Yeah, then it matters. If there's more than 2, then then more than 3, sorry. If there's more than 3, it matters. So is this a violation of Hund's rule?
Yeah.
Yeah, this would be higher energy. This is okay for an excited state, but not okay for the ground state. So this is not good. is this okay?
Yeah.
Yeah. Now, if we have a fourth electron, we have to pair it. This is called pairing. Pairing would be +1/2 and -1/2 here. And so if we have 4, this is okay. But we would not pair it before. So for example, is this okay? Now this would be a violation. So when we fill the orbitals with electrons, then we just count the electrons. So filling orbitals, we need to do that here. So starting with hydrogen, hydrogen is either one electron spin up or one electron spin down. It doesn't matter. Hydrogen doesn't care if it's spin up or spin down unless you put it in a magnet. If you put it in a gigantic magnet, then it makes a difference, and we have magnetic resonance imaging, MRI, or nuclear magnetic resonance, NMR. And so we put that there. This would be hydrogen, and then helium would have 2 electrons. Where would the second electron go for helium? Would it go to the next higher, to the 2s? No, it's too much of an energy jump here. And that would violate off-bow. So what it's going to do is it's going to go here, and it has to pair. Lithium is going to have a third electron. Should I put the third electron in the 2s, or should I put the third electron in the 2p?
2s.
I'm going to put it in the 2s because the 2s orbital is more penetrating, less shielded than a 2p. In other words, it's going to be lower in energy. And so it's going to go here. It doesn't matter if it's spin up or spin down. Now, for the second electron, should I fill it over in the 2p or should I double it up in the 2s? I need to double it up here, because this is an energy jump. Now, for boron, I have 1. I can pick any of the 3 for this. Usually pick the first one. For carbon, I'll have another one. That would be carbon. And then nitrogen would be there. Okay. Now, for oxygen, what do I have to do? I have to double any of these 3 up. I'll just do the first one. It's easy. That's oxygen. And then for fluorine, and then finally for neon, it would be like this. And so helium fills the first shell. And then neon fills the, oh shoot.